Welcome to Brain Vision.
In this example, we're going to be looking at two different gases that have the same density and the same pressure. If you recall, density is mass over volume. And these gases are composed of different molecules or atoms. One is made of helium and it's at 175 degrees Kelvin, and the other is neon, but we don't know what the temperature is. So the temperature is what we're going to try to figure out. So the place we're going to start is with the ideal gas law, since we know these are ideal gases. And I'm going to write one ideal gas law for our helium over here and one ideal gas law for our neon. So for the helium, we'll have PV equals nRT. I'm going to put a subscript on the T because this is the temperature for helium. I'm going to put a subscript on the number of moles, again, because it's specific to helium. And same thing for the volume. I'm not going to put it on the pressure because that's going to be the same for both gases. Now, if we do the same thing for neon, we'll have PV neon equals N of neon times R times the temperature of neon. Okay. So notice these equations are in terms of volume and moles here, which is something we don't really have information on. But what we do know is that the number of moles and the volume are going to be related to this density here, right? Because density is a mass over a volume. And of course, the mass of our substance is going to be related to the number of moles of our substance. So let's work that out specifically. We know that density is m over v, and little m is related to the number of moles by the molar mass. So little m is the number of moles times the molar mass, big M. So if we substitute that into our equation here, we'll have little n times big M over big V. So actually what we can do is we'll be able to substitute out for N and V here in our ideal gas law in terms of the molar mass and the density. So to show you exactly what I'm talking about here, imagine we divide, or actually we'll just go ahead and do this. Let's divide both sides of these equations. Well, actually no, I'm making more work for us than I need to. Let's take our equation for density here. So density is Nm over V. And what I'm going to do is I'm going to keep the moles and the volume on one side, and then I'm going to keep the molar mass and the density on the other side. So if I divide both sides by the molar mass here, I will have rho over m is equal to N over V. And so now, if I make a N over V in our ideal gas law, I should be able to just switch it out with rho over big M. And of course, these will all be subscripted for the specific gas we're talking about. So let's take our equation for helium up here and do exactly what I just mentioned. So P V for helium equals N for helium times R times T for helium. And I want to make a N over V. So I will divide both sides by V. And then I can substitute this out with rho over the molar mass of helium. So rho R T for helium over V for helium. And we did this because, times the molar mass of helium. So we did this because the molar mass of helium is just a constant we can look up, and the density is going to be the same for both gases. So if that's the case, we will only have the unknowns, pressure and density, in our two equations, but we know they'll be the same for both of the setups. So if we equate them, we could probably solve for our temperature. So let's clean up this equation a little bit. It's P equals rho RT over the molar mass. So imagine we did the exact same thing for our equation for neon. We would have pressure of neon equals rho RT over the molar mass. And again, remember, pressure and density are the same for both of these gases. So if the pressure and the density are the same for both gases, that means I can equate them to each other, or equate these two equations to each other, right? So we could do that a couple of ways. I could divide both sides of these equations by rho, and then set P over rho is equal to P over rho. Or honestly, I could just say pressure is equal to pressure right now and equate these things. So I'd have rho RT times helium over the molar mass of helium equals rho RT of neon over the molar mass of neon. And you can see that we have a rho and an R on both sides, so those cancel out. And what we're left with is a really nice equation, which just relates the final and initial, or the temperatures of each gas to their molar mass. So let's remember what we were trying to do in the first place here, which was solve for the temperature of neon. So let's do just that with our equation. So we'll multiply both sides by the molar mass of neon, and we'll end up with the temperature of neon is equal to the temperature of helium times the molar mass of neon over the molar mass of helium. So we have the temperature of helium. So we just need to look up what these molar masses are. So for neon, I found 20.18 grams per mole. And for helium, I'll be using 4 grams per mole. So if we divide those by each other, we can see all the units will cancel out. And we'll just have some number times the temperature, which is 175 Kelvin. And if we do that, our final calculation will give us 883 Kelvin for the final temperature of neon. So there was a lot going on there, but let's just do a quick review of what happened. Given that we had two different gases at two different temperatures, volumes, and two different amounts of moles, but the same density and pressure, we were able to figure out what the temperature, the unknown temperature of one of those gases was. So really, sometimes you just have to kind of work around with what your knowns and unknowns are in the ideal gas law here to try to isolate a single variable.